Welcome to our first lecture of machine learning series in which today's topic is linear regression and gradient descent. Let's go to our tablet screen to discuss more about it. Before starting our today's topic that you can see which is linear regression and gradient descent, first let's discuss what is machine learning. Machine learning. Okay. So let's write the definition first. Machine learning is a subset of artificial intelligence. Here I am going to write AI, which learns the pattern, the pattern, pattern from the data, from the, let's write, highlight the data word. Going to discuss about it in the future part of the lecture and predicts, sorry for the spelling, predicts the future unknown known variables. Okay, so let's read the definition one more time. Machine learning is a subset of artificial intelligence which learns the pattern from the data and predicts the future unknown variables. Okay, so today's topic is, firstly we are going to discuss what is linear regression. Linear regression is a basic machine learning algorithm. Everyone who starts studying machine learning first learns this algorithm which is called linear regression. Okay, so l- according to the definition, we need a data set. Okay, so let's firstly design a data set. We are going to design a data set which has house size and its estimated price. Okay, so if the house, let's just firstly write the, define what the data set will be. House, let's make it more in a beautiful way. House size, HOUC, house size, price. Okay. Uh, let's do it in a beautiful way. This is my beautiful way. Okay. For example, if a house is of 1000 square feet, let's say its price is once, tens, 100,000, 10,000, 100,000. Yeah. $100,000. If the price increased to 1200 square feet, let's say its price goes to once, tens, 100,000, 10,000, 100,000. Yeah. $110,000. If the house size is 1400 square feet, let's say its price is, let's do not follow the pattern here. Let's change the price to $125,000. Okay. If the house price, for example, is here 1600 square feet, again, we are not going to follow the pattern. Let's change the house price to $150,000. Okay. As you can see, we have the data set. Okay. If we want to know what will be the price of 1800 square feet of a house, we are not given the price. We have to predict the price. What we will do, we will apply machine learning on this data. Okay. This is the data we know. Okay. This is the data we want to predict. Okay. So for starters, we are going to use linear regression on this data. Okay. So what is linear? It's first, let's draw this data on a graph. Okay. Uh, Sorry for my presentation skills. Okay. What we should take? I'm just thinking about the numbers that I'm going to write on the graph. Uh, let's start with a king. Okay. Sorry for the inconvenience. 0. Let's start here with house size. On the y-axis, no. On the y-axis, we are going to take price. Okay, price. And on the x-axis, we are going to take the house size. House size. Sorry, a new page was created. House size 500. No, let's take from 1000. Let's suppose here is a king. Okay, let me denote it with a red sign. And here also price starts with $1,000, $100,000. Okay, dollars. Let's write the price here so that it will be easier for us to draw the graph. 1000 and next one is 1200. So we will write 1200, 1400, 1600, 1800. Okay, just wait for a few minutes. Everything will make sense. Okay. 110, comma 000 dollars. It is a very easy topic. Dollars. 130, comma triple zero dollars. Let's say the price have went to $1,500. So we have to increase the size of y-axis. Sorry for the delay. 440, triple zero, $150, triple zero. Let's move the graph a little bit down. Hmm. Uh, yep, like that. Oh, house size. Let's increase the size of y-axis a little more. Dollar 60, triple zero, 170, triple zero. Okay. Now let's see what is the actual values here. So for 1,000 square feet, it is 110, $100,000. Sorry. Okay. For 1,200 square feet, it is $110,000. Okay. So here. Yup. For 14,000 square feet, 1,400 square feet, it is $125,000. 125,000 at the middle part. Yup. For 1,600 square feet, it is $150,000. It is $150,000. Let's reduce it to $140,000 because we want graph to make sense also. Okay. Well, $40,000. Okay. Now we have to predict for $18,000. Okay. So first, as the title suggests, linear, we are going to draw the best fit line. Okay. So for example, we draw the best fit line. The line should be linear, that is, line should be straight. Okay. We have to draw the line such that the errors are minimized. Errors are, for example, this small part. Let me draw it with red. Okay. This, this. These are errors. Okay. So we have to draw the best fit line such that these errors that are denoted in red are minimum. Okay. Let's see some notations before proceedings. So h of theta x will be going to be our predicted value. Predicted value. Y will be our actual value. Actual value. Theta naught, theta 1 dot 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 till theta n will be our learnable parameters. Learnable parameters. Sorry for the bad handwriting. Parameters. X1, X2 dot 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 Xn will be our features. If this do not make sense, no worries. I am going to explain it in the later part of the lectures. Features. So what are features? Features are For example, house size, which is going to determine our predicted value. Here we can also the house price can be determined by a lot of factors. For example, number of rooms, the number of rooms. This can also have, sorry for I do not want to cross it. I want to just highlight it. So these things can also have an effect on our predicted value, that is price. Okay. So for now, we are only considering house size. We are not considering number of rooms or number of bathrooms, number of tiles, whatever you want. So for now, we are going to considering house size for our easier calculations. Okay. Predicted value, actual value, and these are the learnable parameters, theta naught, theta 1, dot dot dot, theta n, which are going to be learned by the algorithm on our data set by performing some calculations on our data set. Okay, so let's calculate cost function. Cost function. So what is cost function? Okay, so let's return to our previous topic. So here our goal is to minimize the errors, these red lines. Okay. So the summations of the average summation of these red lines are our cost function. Okay. Okay. Cost functions. So cost function will be our h of theta x, which is our predicted value minus y. Okay. This is not the whole cost function. Let me be very clear. Okay. So the actual cost function, which is there, of this algorithm. I'm going to explain it. Don't be frightened by it. Let me just put it down. Oh, I don't know why N is selected. From uh, from j j is equal to 1 to n m 1 upon 2m. Okay. So let's take a seat and discuss what is this cost function. Okay. So this is our predicted value as usual. This is our actual value, which is this, these white lines, white dot, sorry, not lines, white dot. This is the y. Why we have done the whole square? So that this value, let me highlight it in red, this value always remains positive. That is why we have done square. As we know, the square of negative numbers, for example, minus 2 whole square is positive. So square of it is a property of maths. For them who don't know, square of negative numbers is always positive. Always positive. There can be a scenario where the predicted value is lower than the actual value. So this, the quantity that is written in bracket can be negative. So that is why we have done squared. Okay. So what is M? M is the number of training examples. Training examples. First of all, I want to tell you, if you are unable to understand some topics in this lecture, don't worry. In the next lecture, we are going to see the practical implementation that is in the Python code of this algorithm, which is linear regression. Okay. So number of trainable, not trainable examples. Examples. Okay. So what are trainable examples? We instead of writing here trainable examples, we can also write the size of the data set that is going in the training set. Okay. If you don't know what is training and test set, don't worry. I am going to discuss it in the next lecture. But for this lecture, we are going to see only the mathematical institution of linear regression. Okay. In the linear regression, gradient descent is also been used. So that is why in the topic I have written gradient descent. Okay. So where I was, number of, yeah. So here, the value of M will be 4 because this is going in our training set. Training set. So this is the size of our actual data that is present for training. So here M will be 4. And first of all, let me explain it step by step. I'm not removing 2 because, uh, let me tell you, 2 is there. Okay. So first I want to explain why there is 1 upon M. The 1 upon M is there to make this, to make to take the average of this cost function, we have to multiply it by 1 upon m. If someone don't know what is average, let me tell you. The formula of average is equal to, for example, there are 5 data points, n1, n2, n3, n4, and n5. So if we want to calculate the average of all the data points that are present, I'm just taking a small example here to explain you what is average. So if we want to calculate the average of these data points, average. So what we will do? N1 plus N2 plus N3 plus N4 plus N5 upon 5. So the size of the data set. Okay. So in this small example, the size of the data set was 5. So that is why the denominator here is 5. But in this cost function, the size of the data set is m. So that is why we have multiplied the whole cost function by 1 upon m. Okay. So I hope the concept of average is clear. So let's erase this. Erase this. What is happening to my pronunciation these days? It is taking a lot of time to get erased. Okay. Okay. Finally, it is erased. Okay. So in the original cost function, there is multiplication of 1 upon 2 also. Let me explain you why. If you have ever okay. Let me erase this also. I have forgotten to erase this. Okay. Let me repeat. In the original cost function, there is also multiplication of 1 upon 2. Why? For easier calculations. Let me tell you why. If you have ever studied differentiation here, because we are going to use differentiation in this particular algorithm. So if you have ever studied differentiation, the differentiation of x square, d of x square by dx, dy is 2x. So what is actually happening? Let me explain you with a generalized example. Okay, so the differentiation of x raised to the power n is n comes here, n, x remains at its place only, x, and in the power there is a subtraction of 1, n minus 1. Okay, no issues, no worries. I hope so. Okay, so here in our original cost function, there is a power of 2. Okay, so when we will differentiate it, 2 will come and will get multiplied by our cost function. So to remove this extra calculation of multiplying the whole function again by 2, we are multiplying the cost function by 1 upon 2 to neutralize that effect. Okay, I hope so it is clear. Okay, yeah. So this whole, let me highlight it with another color. Taking blue for the first time in this video. Okay, let me redraw it. Now our aim is to minimize this cost function. Okay, so this, let's write here cost function. This whole is a cost function. Cost function. Okay, let's think. Okay, now let's look deep in this function. This function is a quadratic function. What is the graph of the quadratic function? If you don't know, I will tell you. The graph of the quadratic function is a simple parabola. Okay, the graph of the quadratic function is simple parabola. So let's assume for this example, the graph of this cost function is this. Okay, the graph of this cost function is this. Okay, so our whole aim is to define the values of the learnable parameters in such a way that the value comes here at the minima of this function, or at the minimum value of this function. So now we are going to apply gradient descent. See here. Okay, so now we are going to discuss gradient descent. So let me write what is gradient descent first, then I will explain you in the later part of the video. Repeat. Theta j is equal to theta j minus alpha of. I am just writing this I will explain it. Don't worry. I will explain. I know it looks like a little bit complicated. It looked to me also. So no worries on that. Okay. So this is the whole algorithm of our gradient descent. Gradient descent. DESCENT. Sorry if there is any error. If there are any spelling errors in this video, please, I'm sorry for that in advance. Okay. So let's discuss. What is theta j? So theta j is our learnable parameters. Learnable parameters. Parameters. Okay. What is j here? Okay. So j here is the number of learnable parameters that will be present in our function. For example, I know this is a little bit complicated. For example, in our original function, in our original example here, since we have only one feature, so the will be theta naught plus theta 1 x1. So this is the bias term. Or if you don't want to go in that complexity, these both are our learnable parameters. For this example, learnable parameters. Okay, parameters. And this is our feature. If this equation doesn't look familiar, let me write the one equation that is very much familiar to you, which is y is equal to mx plus c. In your schooling, you must have heard about this equation. Okay, so what is this equation? If any one of you don't know, so y will be our predicted value, predicted value. M is the slope of this line, slope of this line, slope. And C is the intercept. And X is this simple. Okay. So J can be 0 and 1 for this example. Okay. So it depends on the learnable parameters we are working on. So J is that learnable parameter we are working on. Okay. This theta j and this theta j are same. What is alpha? Alpha is learning rate. Learning rate. This is not a learnable parameter. This is a hyperparameter. This its value we will set well in advance. For example, let me tell you. The value of this, which is theta, is getting calculated by our algorithm. But the value of alpha we are going to set well in advance before running this algorithm. Okay. For starters, we set this learning rate equal to 0.01. I will tell you in detail about the learning algorithm in the later part of the video. And j of theta is our cost function. So here we will write cost function. So j of theta is our cost function. Okay. Oh, okay. Here there is differentiation of this cost function. Okay. So in the earlier part of the video, I have told you we are going to differentiate this cost function. Now, in the gradient descent part, we are going to differentiate this cost function. Okay. So let's understand gradient descent in a more advanced way. For example, the cost function of, let me denote it with red or draw it with red. For example, our cost function is here initially. Okay. So what our gradient descent do is uh, help this cost function to obtain minima. Okay. So if the value of the, I think so it is clear, because we all know the slope of the line is the differentiation of the equation. See, the differentiation of a positive slope is always positive and the differentiation of a negative slope is always negative. If we see this line, if we draw a tangent, let me draw it with white. If we draw a tangent, this is not a tangent. You assume there I have drawn a tangent. Okay. So if you observe the tangent, it will have a positive slope. So the differentiation of it will also be positive, resulting it coming down. Once again, we will repeat this algorithm. You can say I have written here repeat, repeat, repeat. We will repeat it until the algorithm until the loss function converges. Okay. So the one question that you should have in your mind is till how long we will run this gradient descent. Okay. So there are two rules for this. First rule is you can set the number of times the gradient descent can run. Okay. You can set it 1,000 times, 100 times, or you can set target value. For example, the difference between this, let me note it with blue. Difference between this value and this value should be greater than a target value. If the difference between these two values are lesser than the target value, then we will stop the gradient descent algorithm. Okay. So this part is, I think, so clear. Okay. So now we will discuss about the learning rate. Okay. What is learning rate? Here we have set the learning rate is of 0.01. In practice, if you go in the industry, we set the learning rate is equal to 0.01. Okay. For example, what will happen if we do not use this hyperparameter called learning rate? Think about it. The our loss function, instead from going from here to here, it will go here. Understand the point? Instead, the loss function is let me change the loss function should go from here to here. But if we don't set the learning rate, or if we set the learning rate very high, for example, 1,000, 100, loss function can go from here to here. It is definite. If you set the loss function 100, it will definitely go here. But for instance, if you don't set the learning rate, if you don't set, it means the learning rate is 1. Then the learning rate can go here. It means it can jump to and fro, which can result in never convergence. That is, there can be a possibility that the loss function never converge. So that is why we set the learning rate is equal to 0.01. So here is the whole algorithm of linear regression and gradient descent. I hope you like this lecture.